These Calibrations, you guys probably see these guys all over. They're phenomenal. We've been working with these guys for what, probably 8, 10 years. They probably calibrate most of your guys' stuff. They do a lot for our organization. I appreciate you guys, and it's your guys are up.
Thank you. I appreciate you guys. Appreciate everybody else in here too that has worked with us over the years. It's sincerely, we appreciate it very, very much. It's a family business, and the guys that work with us are kind of family oriented, so it fits perfectly with you guys, I think. So thank you. So calibrations and controls. We started our business about almost 30 years ago. It was First Systems Technology, and we did integration, SCADA, telemetry. We did all the PLC work, everything. But as time went on, our calibration work, our troubleshooting and repairs started accelerating, so we started to niche down and focus on that work. So at that time, we changed the company name to Calibrations and Controls. I started in automation, I guess integration. Went to school in like '84. Went to work for IOB Processors, which Tyson bought out, did automation for them, started up 4 plants in 5 years for them. Not just me, but the whole crew. Learned a lot. I mean, massive amount of information. Then I went to work for an engineering company that I used to buy equipment from, and they were an integrator. And then for 5 years, I worked with them under 10 engineers doing quality control. And I learned so much, because every one of those engineers did it right, but they were all different, you know, right? But I got to learn from every single one of them, and I could pick and choose kind of what I thought was best. Now I know what's best instead of them. But that gave me a good start in the business. In that 5 years, I learned more than a lot of people would learn in 10 or 15 years, just because it was 10, 20 panels a day that we were testing and sending out. So I learned a massive amount in 5 years. And then I went to work for a small company called Bentech Engineering. They were one of the big players in water wastewater for a long time. I didn't know they were going out of business. The last year I worked for them, I didn't know that until they went out of business. And while they were going out of business, the bank called the loans due and said, hey, we want you to finish these jobs and we want you to stay. And I said, okay, but I'm going to start my business while I'm doing that. And that's when I started it in 97, 98. So that's kind of the background of myself and how it started, and just kind of kept growing, and the different paths we take in life to get to where we are. So we have quite a few different, most of we started out in the water wastewater. But as time's gone on, we've increased our abilities and made things better and better and better. And now we're starting to do a lot of work for industrial too. Tuffy's is KLN, Aurora's a pharmaceutical for pets, Pet Plus is another one. XL Energy we do some work for, so we're starting to branch out into other areas. This is a new presentation today, so I'm going to have to kind of look at it once in a while and do it at the same time, because it's brand new. We finished it last night and this morning, so it's going to be kind of fun. But so our company, we do calibrations, repairs, installation, and troubleshooting. We're also a partner with MRWA, like Joe said. We're a Ruby level partner, so we're trying to be kind of involved with you guys, help with the training and do all these different types of things, and then hopefully we're working together and accomplishing the same goal. So the things we're going to hit today, in the past I had one where I talked more about calibrations, more in depth of each different type of meter. Today I'm going to talk more about the regulations and just kind of an overview of what instrumentation is and how it works in your whole system. So we're going to talk about the instrumentation, what it is, MPCA requirements, and then also calibration verification, what the difference is, and how some of it's performed. So why instrumentation matters. So in our plant, we're always trying to make sure everything is balanced and equal. After it's coming in and then going out, we're trying to reduce, I don't know what to call it, PODs and different things, and keep your flows as steady as possible to keep everything running smoothly. And then chemical feeds are based off of flow and pH and DO and all these different things. So all these instrumentations are telling you what is happening so that you can make decisions and know what to do. So if those aren't right, then you're making kind of guesses, and then if you test it, you say, well, I got to adjust that a little bit. But if it was right, you wouldn't have to do that. It'd make your jobs a lot easier. So that's the importance of calibrations and making sure that your instruments are right and doing the job they're supposed to be doing when they design the system. It's also for protection because you wouldn't want to put too much chlorine in or too much fluoride if you do water systems too. All these different things. So it's all this stuff comes into play with the instrumentation. So what is instrumentation? Instrumentation is all the devices that do flow, temperature, conductivity, pH. I know I'm probably missing some. All these different things they consider instrumentation. And the instrumentation pulls that actual real-world process information and then makes a decision on it and then gives you an output. So think of it as you hear something or you see something, then your brain has to change it and do something, and then it speaks it out. So that's the seeing the flow in the water, and then it manipulates that data, and it comes back out as a 4 to 20 go to your system so that it can respond to it, chart it, trend it, record it, totalize it, all those different things. So that's basically what all instrumentations do, and I don't care if it's pressure, flow, temperature, pH, whatever it is, they all do basically the same thing. And this is some examples of different equipment: pressure, flow, temperature, level, conductivity, turbidity, dissolved oxygen, DO. And then this is basically just a list of those in a different way. Ultrasonic sensors for open channel flow meters that you're usually on your influent, sometimes on the effluent too. Mag meters, propeller meters at your water plant. A lot of times the older meters are propellers because you don't want to have those on dirty water because they collect stuff on the propeller. A lot of the propellers are starting to go away as they go bad and they need to be replaced. People are putting in mag meters now. We probably do 20 to 30 mag meters a year, replacing existing meters. pH, you make sure your conductivity or your pH level is correct before it goes out. DO to make sure that there's enough oxygen in the water before it goes out. And then this is just a picture of some different ones. So that's a sensor of a mag meter, and that could be conductivity, that could be pH, that could be temperature. They're basically all the same instrument, just how it's set up and programmed to do the job you want it to do. Anderson-Hauser mag meter, another Anderson-Hauser, Badger, ABB, these are Yokogawa, and a Rosemount Coriolis meter. Coriolis meters are very, 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 very accurate. You won't see that in the water industry. Usually in pharmaceuticals, they're like 0.01 accuracy. A mag meter is about a half, so 0.5. So big difference. So if you had if you had a mag meter 4-inch and a Coriolis, the mag meter list would probably be around 5,000 to 6,000. A Coriolis 10,000 to 15,000. So a big difference, and it's not necessary in the water industry. So what do these instruments do? So the instrument reads the real world variable, we call it a process variable, whether it's water, flow, temperature, conductivity, pH, whatever it is. So it reads that. And then once it reads, so this is the, say, a flow meter, and this is the sensor, this is the transmitter. And then once it figures out what that is, it translates that into a 4 to 20. So if you're saying it's 0 to 1,000 gallons per minute, that 4 to 20 would now be calibrated 0 to 1,000 gallons a minute. And so would your PLC, and so would your SCADA, whatever it's going to, so everything's the same going through. It's like speaking English and you can understand it. If it's not, then it's not going to read it right, it's not going to trend it right, it's not going to totalize it right. Nothing will be right. So there's a lot of people that go out and do calibrations. I'm kind of jumping it a little bit here, but they'll do calibrations, and the only thing required is to do the input part of it. So if you do a calibration on the flow meter, and you just did the input part, but the 4 to 20 is not right, you're only halfway there. You don't know. So we try to do that whole, I call it the whole flow, all the way through the whole thing, to make sure it's right. So that 4 to 20 comes out, can go to a PID controller, that could be a PLC, that could be a SCADA, whatever it is that makes the decisions to operate your plant, whether it's a valve opening and closing, whether it's feeding chemicals, whatever it is. All that stuff has to be zeroed and spanned, they call it, correctly in order to work properly. And then I think this is just another example of that. So you got the flow meter here, you got a valve, so the flow meter's telling what the flow is, and based on that flow, you got some set points that you set. And this could be a water tower, same thing, pump start and stop, fill a water tower. They don't do PID, they just go on off at set points like start stop. But some of the newer ones are doing PID, and a PID would be a set point, and it will try to hold it there. So as the water gets closer, it slows it down and tries to hold it there. And then as the water drops, it speeds it up, and that's called a PID. So it's called proportional. As it drops, it increases the speed, and as it increases it, as the water increases, then it decreases the speed of the pump. So that's basically what this is. So then that output would go to the valve and tell the valve to open or close, or the pump to go faster or slower, or whatever it is. And that's a whole loop. They call that a loop for control. So magnetic flow meters, basic components are usually you'll have a transmitter, and that's usually where the readout is. That's kind of the brains. So that's the transmitter, and then you have the sensor, which is actually in the line or reading the pH or the flow or whatever it is. So you have the three parts to it. You have the sensor, transmitter, and then the 4 to 20 out, which would go out of the transmitter over to your system so that it can make decisions based on that. And that's what I'm talking about. We do a full calibration. We not only do the flow part, we also do the 4 to 20 out of here to make sure it's correct going to the PLC and whatever the chart recorder, whatever device it's going to. Otherwise, you're only halfway there. If, for example, if this was 0 to 1,000 gallons per minute, and your PLC was set for 0 to 2,000, when you're at 1,000, it's only going to be showing half the flow because it was set for twice as much. So, and that's an extreme, but that's a good example. And here's another one. This is it could be pH, or P, whatever it is. Again, basically have the same thing. You've got the sensor, you've got the transmitter, and then you have the 4 to 20 out to your system. Basically the same thing. So all instrumentation is basically the same, even though it's totally different. So magnetic flow meters are about 0.5%. In our industry, about 0.5% accuracy, almost all of them. They'll say 0.4, some will say 0.5, some will say 0.6. They're basically 0.5%. Everybody's trying to sell something, so they say it's a little bit better because they saw it one time it was like this. So, but they're all basically 0.5%. And that's normally, that's waste efficient in the water and wastewater. The old propeller meters, 2.5 to 5%. So big difference in your water. So that's another point with propeller meters, and now you've got your new meters in your houses that are ultrasonic, and they're very accurate, but your propeller meters aren't, so it could either be high or low by quite a bit, and you wouldn't know if you're losing water, somebody's taking it, what's going on there, because there's two different accuracy meters in your system. So level and pressure devices, you have pressure on your water towers that tell you the level on your water towers, and then you set your start-stop points to fill the tower and tell your pumps to start. You have pressure transducers in the lift station that are submersible, so they're down below and they're telling you how much water is on top of the transducer, and then that tells the pumps to start and stop. You can also use ultrasonic. Lately I've been seeing more pressure than I see ultrasonic because they can sometimes get a film on them and stuff. But ultrasonic can also read down and tells you how high the water is. So ultrasonic can do two things. It can read down and tell you how far it is away, or you can reverse it and have it set to 0 at the very bottom, and then you can tell it how high the water is in the device or whatever product it is. Water quality analyzers would be, again, they're just instruments, DO, pH, ORP, lots of different instruments, temperature, conductivity, a lot of different ones that test the quality of the water to make sure it's suitable to go back out to the river, the creek, or wherever it's going. So the SCADA trap, almost what I was just talking about. So if I have that flow meter, and I always talk about flow because everybody's got flow. So if we have that flow meter and it's set up 0 to 1,000 again, but your SCADA is set up 0 to 2,000, it's not going to display right because your span on the SCADA is twice as much as the flow meter. So when we first go out and do meters or do a calibration of any piece of equipment, there's two things we do. One of them is we try to check the host system as well as we can, because sometimes the documentation isn't there. But we try to test the host system as much as we can. We do that by simulating with our equipment, find out what the system's supposed to be doing, and then we work backwards to make sure that that device, that instrument was set up correctly for 0 and span, and that correct information is now being sent, whether it's through a radio, PLC, whatever it is. So we make sure that whole system is correct as well as we can, and we document it so that if something happens in the future, we've got the information to replace it or troubleshoot it or get it back up to where it was before. So then after that, we don't do that unless you see a problem. But the first time we try to go through the whole thing, document it, and make sure it's correct. So now we're into the MPCA requirements, and most of you guys probably know this stuff, but we're just going to kind of go through it because it's very, very important for especially a wastewater plant. Because your influent, effluent, everybody's license is a little different. How many times do you have to do your influent or effluent meter of both per year at a wastewater?
Twice.
How many? 2. That's right. Where's our cups at? We should give him a cup. We got some cups here, so if anybody asks a question or answers a thing, we'll give you a cup. But are they way back there?
Yeah, they're way back there. I'll
Yeah,
grab them.
let's do that. So I like questions. I might not be able to answer them, but I still like them. So MPCA is our governing body telling us what we have to do to meet the requirements. And like you said, the influent, effluent, or both, depending on where it is, have to be done twice a year. The water plants don't have that requirement yet. They expect it to be done at least once a year, but they haven't required it yet. I'm sure it's coming. You guys have seen all the stuff increase over the years, your drawdowns and all your different things that you have to document. So the guy in the second row there.
Only just pass them out at the end.
I don't know if there's enough.
Who was it? Sorry.
So the first, I don't know if there's like 8 cups. They're really nice double wall, like the Stanleys. So,
I have a question.
okay.
Can I have a cup?
No. Has to be legitimate. May I please have, no, he has to go. No, it was funny. You can give it in. I knew that was coming.
It's pretty easy. 5 left, so.
5 left. All right. By the way, I learned that. Well, I won't say where I learned it. The no. Okay, so what the MPCA wants to do, not everybody has a flow meter. Some people have a lift station and all it's doing is pumping. There's all different types of things. So they want to make sure the flow meters are tested twice a year. Your pump lift stations are timed so that we know what the flow is per minute, so that you can look at your run times and then gather that. We do those. The flumes, which is usually your opener, or your influent or effluent, make sure those are correct. And then lift stations is kind of with the pumps.
Is that on your permit then?
Yes, and I've never seen the permit actually, but Joe and those guys would be better to ask where it's at on your permit, but it is listed on there. It tells you how often you have to have it done. Yeah, I don't know who asked that question. Right there. Yeah, you want to give him one?
You get him up? You get him up?
What's that?
You get him up?
Yeah. Yeah. No. Yeah. No, it's cool. Yeah. Yeah. MRWA will be able to help you with where that's at. So a lift station, I kind of went forward here, but I'm going to go back one. So a lift station, basically what you're doing is you're timing when the pump starts.
Go back one more.
Yep, did I?
Oh.
So when the pump starts, we start a timer and we get the level, and then when it stops, you get that amount of time you stop the timer and get that distance and figure out what the volume is and how many gallons per minute it is. And then you also, if your flow is significant, we also watch the water coming in at that time so that we can add that to it. Because there's always a little bit of water coming in while it's pumping. So there's some coming in and trying to pump out at the same time. So we try to gather both at the same time as fast as we can. We use ultrasonic and timer, so we're very, very accurate with it because we don't drop anything down, measure it, then lose time, and it's very fast and very accurate. And then you take that gallons per minute, and then you can take it times your run times for each pump and figure out how many gallons you pumped over a period of time. The thing about drawdowns is I did it this time, but the next time there could be flushables. And now you're not going to get as many gallons as the last time. So there's all different things, and over 6 months you know that pump is not the same as it was 6 months ago. So it's always a little, but it gives them the best you can with what you have. So the MRWA requires that you keep records, and you have to keep these records for 3 years.
MPCA.
MPCA, I mean, what did I say?
MWA.
Oh, MPCA.
Yeah.
MPCA requires you keep them for 3 years, and it has to show who did it, when they did it, and it has to be signed, and then you guys have to keep that documentation. We keep that online. As long as you're a customer of ours, we pay for the website and storage and all that kind of stuff, and it's there. All you do is go out to the site, and by year, all your calibrations are in there in order, by date and asset. So we have asset numbers for each one, which is like a serial number to us, and they're all there, documents, so it makes it really easy. You can go look at them anytime you want. Somebody asks you a question, you can send them the link, you can download them, print them, do whatever you want. From your phone, tablet, computer, whatever. Another requirement, person who falsifies, tampers with, or knowingly renders a monitoring device inaccurate or purposely conducts an inaccurate testing method required to maintain coverage under this agreement permit is subject to penalties provided by federal or state law. You guys are all, from what I understand, because I don't know the whole thing, but when you do this and you get your license, you're now personally responsible. Which is a big deal. I mean, that's kind of a big deal. You don't hear about people getting in trouble very much, but you can. But it's very, very important. So I know, I'm not going to name or anything else, but I know there's some in the past where they say, yeah, I can give it to you. And there's really no way because there's no straight pipe, there's no flow meters, nothing, but they still will give you documentation. It's probably right on that gray line. We won't do it because we know it can't be done, so I won't jeopardize me or you. So that they consider that a criminal activity if you do that knowingly. I think there was something in Florida where something happened to somebody that they fed too much chlorine or fluoride or something. They actually got in trouble and got jail time, if I remember right. You guys probably heard about that.
Michigan.
Michigan?
Yeah, Flint, Michigan.
Oh, Flint, that was a
That
big deal.
was huge.
There was another one, I think, in Florida too, where somebody gained access to it and did it. And they got a past employee or something. Something like that, but yeah, Flint, yeah, that was big one. Yep. So it really is very, very important. So what are the key points or requirements? So they're the regulatory body, which we all know. They're the ones that set the rules and tell us what we have to do and what we can't do and all those types of things. And the purpose is to make sure that things are as accurate as possible so we know what water's coming out of the ground, what water's going back in. I think, if I remember right, I remember way back when water was going back into the rivers, didn't have enough oxygen, it was taking up the oxygen in the rivers and the fish were dying. It meant there's too much chlorine, it was killing all the growth, so now you have to take it back out. So there's all these purposes for it. It seems overkill sometimes, but I guess we're all trying to live harmoniously, you know? So there's, somebody sees a reason for it. Frequency, back to the twice a year on your effluent, and some of the other ones have some other requirements too, depending on your permit. Documentation, we talked about that. You have to keep it for 3 years. We have it online for you as long as you're a customer, but you can print it, you can save it, you can download it, you can do whatever you want. And this is kind of just a little thing that you can look at it online. So you go to the website, and some reports are going to look like this, some are looking like this. This is the more involved one where we're calibrating the 420 and how far off it was, with the show graph and everything of it. So we get pretty intense over the years. We've just kind of gotten better and better. The software's gotten better, or what we could do with it's gotten better. I mean, everything's just getting better and better. It's things that we wanted to do 20 years ago, it just wasn't really possible unless you're Tesla or something, you know, with lots of money and lots of computers. That's another example of a report. Look on your computer, or look on your phone, or your tablet, or whatever it is. You can access it basically anytime as long as you've got a connection. So purpose of instrumentation or calibration, we talked about that a little bit. We want to make sure that it's accurate, it's consistent, repeatable, so your flow starts and stops, it repeats back if it's exactly the same flow. Whatever the flow is, your 4 to 20 is correct, so it's telling your chlorine to feed right, your fluoride to feed right, your sodium bisulfite, whatever it is, making sure everything's right, making sure recording's right, DO, whatever it is, making sure all that stuff is correct so you know what to do to improve your system. There's many times where we go out and things haven't been done for years, and this is maybe 10, 15 years ago, because people are getting more on top of it. But when I first would start, they didn't know if anything was correct, so they didn't even know where to start. So we get the meter right, and the flow meter. They get the flow meter right, and then once they got that right, oh, well now I'm seeing this. So then we get that next instrument right, oh, now I'm seeing this. So it kind of keeps going until pretty soon you've got this all in line, and then you can really see what's going on. It does make a big difference for some people that really want to get a grip on it. So the calibration process. So any kind of calibration, you have to have a known standard. Like a scale, you'd have a weight, and that weight has to be, you have to know that it's a known standard so that when you step on the scale, you know it's accurate. Otherwise, if you have a comparative to something, it's called a reference, how do you know it's right? And that's the same with flow meters or whatever. And flow meters use verificators and different devices to do it. But the most important thing is that we have a known standard and we have a procedure to do it. So every time we hit a new meter or a new piece of device, we come up with a new procedure so that every time we do it, we're consistent, we do it the same way. Otherwise, we have 3 guys going out. One does it this way, one does it that way, one does it another way, and then we don't know for sure what the history is and what's happening. So it's important to me or us that we all do it the same way. Not only that, even if it's not quite right, then we can keep adjusting it and make it better and better and better. Because if you call me and you say, hey, I'm having this problem, well, this is what we do and this is how we do it. Not, this guy does it that way, and this guy does it that way, and this guy. We try to do it the same way so that we're all doing the same thing. Makes things more efficient, and then we know what we're doing, and you guys know that we're trying to be as consistent as possible. So then you identify deviation. So whether it's on the input or the output, how much different is it? And then can we calibrate it? Can we adjust it? And then we have to make a decision what we're going to do. And then make adjustments, like I said, and then record those results, which is on your reports. So why is calibration important? We've kind of touched on this already. Not only quality control to make sure everything's right and that you can have confidence in your system, but also compliance, MPCA, whatever else it is. In industry, they got all kinds of food and different ones that we have to match. And then safety to make sure that chemicals are fed right and not too much fluoride, not too much chlorine, all these different things. And then also, if it's not right, you put too much chlorine, it's costing you a lot of money. So we want to make sure all these things are right, to not only for all those other reasons, but also to save money and make sure that you're as efficient as possible. So I kind of talked about this already. An example of a calibration would be at home you have a scale, and you step on it, and it says what your weight is. And you go, I wonder if that's right. You just expect it to be right. But you don't know, because you haven't put anything on it, which is called a reference, to make sure it's right. So you get this reference weight, you put it on. How do you know that weight's right? We send it into NIST, and they compare it to their meteorology stuff. And I don't know how they get it or where they get it or how they determine theirs is right, but somehow they do it. And then we make sure that that is all exactly the same. So when you put that 100 pounds under, it says 100 pounds. When you put 200 pounds on, it says 200 pounds. That goes for flow, whether it's a gallon per minute, 1,000, 2,000, whatever it is. We have different equipment to do different things. pH, you have buffers you put in, you compare it, make sure it's right. Conductivity, we have standards we put in, which are called references, and we make sure they're right. It goes on and on and on and on. So when we get this stuff, we make sure that that stuff has also been tested by NIST, and our equipment's been tested by NIST, so that all this stuff is right. Yep.
Where do you get the standards for all the different?
All over the place. So gas we get from a gas company. Weights we get from different weight companies. The verificators for the mag meters we have to buy from the manufacturer. They've got the testing to make sure that that thing's right, and we can test it in the plant. Our meters we send in, and they've got the standard. They compare our 4 to 20, make sure it's right on. 1 to 4 volts, 1 to 10 volts, whatever. They make sure our equipment's right. So, yeah, there's all different places we have to send this stuff in, and it's very expensive. But we've decided we wanted to be that next level. So we do all those things. So we're probably a little bit more expensive than some other people out there, but we do the full thing, and we make sure that our equipment's been tested. I don't know too many people that go out that have the equipment we have that they have tested every year like that. There's not very many. That there might be like Rosemount has their own, they do it. Anderson House has their own. We have Rosemount, Anderson House, Badger, ABB, we have like 8 or 9 different ones for verificators, so we gotta get all these tested. So yeah, they're all over the place. And then on that report, like if we're doing a LEL gas, we bought standard gas reference, and on it tells a date and NIST and what lot it came from and everything. So now we are assured that that is as good as it can be, and that's what we test your equipment with our equipment that's also been tested by NIST, so we can make sure it's as accurate as possible. And on the report, it will put that gas lot number and everything, so that when we go back, if somebody says, hey, this thing blew up because it wasn't what we can say, this is what we did, this is what we did it with, and it came from them, from this lot. So,
Are you calibrating with actual flow on the mag meters, or is it all in the software?
so there's different ones. So there's 3 or 4 different ways you can do so calibration. Calibration is anytime you test something, even if you don't make an adjustment, they consider it a calibration. I used to think anytime you did it, it had to be adjusted to be a calibration, but it doesn't necessarily have to be adjusted. You still performed it and you checked it and you made sure it was correct. So mag meters is a good example. A mag meter, you got a propeller meter, there's no verificator for it. So there's 2 ways to do that one. One is to do a clamp on and compare it, and the other way is to take it out and send it in and have measured water go through it. That's a lot of work. Take it out, send it in, it gets damaged on the way back, and blah, blah, blah. And then you don't have a meter during that time, you gotta put a cap on it. So we come up with a clamp on it, and if we can't do it, we'll let you know, and if we can't do it, we do it. So that's the verification to make sure it's in. A clamp meter is not gonna be, well, it's gonna be pretty close to a prop meter, really close. If we can get the reading, it'll be really, really close. Sometimes we can't get a good reading, and we know, because we can look at the signals and see whether it's gonna be good or not. Then we get to mag meters, and mag meters, you used to have to take them out and send them in, and they put measured water through them. That's a true calibration. So you'll hear people say, well, you can't calibrate a mag meter. Depends on what your definition of calibration is. If you go by the dictionary, yes, you can, because it's anytime you're verifying and checking it. But they'll say, well, it's a verification. So the mag meter companies have come out with a verificator, because they didn't want to fight that thing. So they call it a verificator. And every brand has a different one, different models. So we hook that up and it makes sure that that meter is exactly like it was when it was first built. So if it was installed right and all set up right and programmed right, it's still good. So it's still considered calibrated. The other way you can do it is with a clamp on if there's not a verificator available. So, and that's my 3rd choice. That's if there's nothing else available, this is what we do, and then we watch over time to see if it changes. So that's another part of the consistency. We want to make sure we did it in the same place, the same setup, so that we can see if things change. So all these little things that make a big difference. But that's a very good question.
Yeah.
You should get a cup.
Yeah. Could you repeat that question one more time?
If you're calibrating with actual flow through the meter, or if it was just in the software.
Yeah. So I guess just to piggyback off of what Brad said, for MPCA requirements, for like he was saying, for like a propeller meter, you could do the ultrasonic clamp on. But really the ideal way to do it would be to remove it and put measured water through it. But for you guys, MPCA doesn't require that just because of all the time and money that would be involved in it. But for a mag meter, we have the manufacturer's verificator, or alternatively, you could put measured water through it. And those are, for mag meters, it's nice because that would be the manufacturer's verificator, or putting measured water through it wouldn't, it's a step above. It's not just compliant with MPCA, but we can do that with industrial as well that have higher standards.
Yeah.
So yeah, just kind of.
That's a good explanation.
Yeah.
So they call it an in situ verification device. So it's in the situation, because people came up with those and they said, we can't be yanking these out and send them in. So they started coming up with these devices that we could test it and make sure it was exactly the same as when it was manufactured. But then I can select 1%, 5%, 2%, 0.5%, whatever, depending on the brand. Every one of
The
them has a little-
verification report is calibrated within the.
Oh, absolutely. Yeah. That's what probably 90% use a verificator, even in industrial. But when you get into pharmaceutical, then they have spares, and they take it out, they send it in, they put the other one in, and then they just keep moving down the line because it's medicine. So you got to do a step above. It can't be any question whatsoever. So otherwise, most of the time, the verification is the way. So that's the way we prefer to do it, unless there's not one available. Then we go to the clamp on.
So
So you're
Totally.
able to work with the SCADA integrator then, or?
Yeah, so then,
Or
so
you're
let's say
able to-
that we, so that's a good point. So if we came the first time and we found out ours is set up for 0 to 1,000, yours is set up for 0 to 2,000, I can give you that information and then you can call your integrator and say, hey, there's two different ways. You can change this or we can change it on the meter, which is the easiest way. So if we find out that it wasn't set up right, we just change it in the meter to equal the system. And then we force it to send that signal through to make sure all the way through it's right. So that's the easiest way to do it, is that we just change it, if we're able to. Yep, that was a good question. Should have one. So who sets the standards? NIST, we just talked about that. They're the ones that send all these standards for all the different pieces of equipment. They do meteorology, they do flow, they do clocks, everything. And that's where that standard comes from. Time, everything. Oh, there was one more thing in there. So normally we do, we try to get it to whatever standards the manufacturer is, but there's also sometimes we have to meet, and it can't be, so the manufacturer is the limit of what that device can do. So then there might be some other governing body like MPCA says within 10%, but the meter is 0.5%, that's easy, right? If we have something that's 0.5% and some governing body in food says it's got to be within 1%, that's still doable. But if they said it has to be better than that, now that meter has to be replaced because it can't do better than what it is. It can only do what it is specified for. So we usually have 3 different tolerances. In the water industry, it's the old standard was 10%, which I think, we read through some of the stuff, and the 10% I don't think was meant for, or we didn't think that it was meant for, the meter can be off 10%. I think what they meant was your flow, like your effluent or your influent, should be within 10% all the time, unless it's in the spring or the fall or the summer or the winter. That's the way we read it. So it's been, in the past it was always 10%, but I don't think that's really what they intended. So we always try to make sure it's way better than that. 10% to me is like throw it away. That's bad. So input-output calibration, we talked about this a little bit. The input is whatever your process is, your water, whatever it is, temperature, pH, conductivity, whatever it is, calibrate that, and then also make sure it's set up right, and then make sure the output is set up right, which is usually a 4 to 20. 99% of them are 4 to 20. 4 to 20 milliamps is set up for 0 to 1,000 gallons per minute, 0 to 2,000, whatever it is, your 0 in your span. It just represents that. Methods of calibration, we already talked about this a little bit, comparing it to a known standard. Like a scale, you put the weight on it, make sure it's right. And if it's not, now you have to calibrate it. If you can't, then you just say it's off by a ½ pound or off by a ¼ pound. Some things you can't change. So then you document what it is. They can change it in their SCADA, PLC if it's important, or you just have notes and then you watch your stuff and make sure it's right. So we talked about this, the manufacturer's verificator, which is usually on mag meters. They have a verificator to verify them. So the number one way, sending it in with measured water, hardly anybody does that. Second way is the verificator, which is what we prefer to do. Third way is the clamp on. And then we do have a test rig that we have a mag meter that actually goes to 1/4%. So we like ours to be a little bit better than what we're testing. So if there's a Badger meter on a big building or something like that, usually they have a test port. You can close the valve, run the water through that test port through our meter, and make sure that that meter is still accurate. So if you have a big customer that's using a lot of water and you want to test that one every year, then we could do that with that test rig. And we do that a lot of trailer courts, a lot of industrial sites, apartment buildings, big things where there's a lot more use. Because they don't measure what's going out, and they have to pay on it, so they want to make sure their incoming water meter is correct. And these are some of the verificators. These are just a couple examples. So this one's for Rosemount. So most of these meters now have 2 ways of testing. One is I call the analog way, which is using a device, and then the other way is digital, which is internal. So the internal is a good check, but I like the analog way if there's a problem because it's something external testing it. Be like if you ask me how you doing, I say I'm fine. That's all I know about myself, right? But if I have something else testing me, it'll tell me the truth. So I like the outside device testing, and we do that as much as possible, but we also do the electronic in between a lot of times because it does more of a this whole thing passed, this thing whole passed, this thing whole passed. So you know your meter's working right. And then if there is a problem, now you bring out the analog and you check it. So there's a couple different ways you do them now. And I call that the analog way, and that's this device. This is for Siemens, this is for Anderson Hauser. So those are just examples. Each one of those, the Rosemont one's a little about 10,000. These are 20,000, and this one's 20,000. So these things are not cheap. Very, very expensive. I don't know anybody else that drives around with all these different pieces of equipment. Like I said, manufacturers have their own, but they don't have all of them. I don't have all of them. There's a whole bunch of them. I just have the main ones that I see around Minnesota mostly. Misconceptions you often hear. It's been working fine for years. I used to get that a lot. Or I didn't even know I had that meter. I used to, way back. So that's one of the big ones. All calibration companies are the same. Well, we know that's not true. I mean, between you guys, not everybody's the same. Between an excavator, not everybody's the same. You know, builder, everything, they're not the same. There's no, I can say I do calibrations this way, another guy says I do calibrations this way, another guy says I do calibrations that way. And some of them are very, very lax. Some of them have 30-year-old piece of equipment and they do one thing and that's all they can do. So we try to be quite a few steps past that basic, I would say. We're starting to do industrial, and industrial gets very, very picky. They have people checking people checking people. So we're trying to go in that direction. So we're kind of making all of our, we don't do different here, different there, or else now we got all these different procedures and different ways of training, and which way do we do this one? Which way do we do? So we try to do them all the same to make sure that everybody is equal and the way we do it is equal. So it doesn't affect plant performance. Well, if it's feeding chlorine and stuff, it definitely does. You know, some smaller plants it doesn't, but bigger plants it does, just depending on what you have. My flow rates are about the same as they should be, or they're this. So here's a good one. So we had an old meter in somewhere, and they said, well, that's not what my flow used to be, but it was never set up right. So they based all their decisions on the way it was before, but we want to snap back. So now we got it right. Yeah, but that can't be right because it used to be this. Well, then maybe we should put your old meter back in, right? Right? But we don't think that way. You know, so it's because we always want, and we tend to do that too. I mean, sometimes I go, well, God, it was this. Well, no, quit thinking that way. You know, you have to quit thinking. You have to do, if you have confidence in what you did and how you set it up and what you're doing, this is now right. That wasn't right. Doesn't mean it was right just because it was that way. I had one where it was an 18-inch partial flume, and we went out to do the calibration, you know, set up for a 3-inch partial flume. I have no idea how they were reading it or making it read what they wanted it to read, but it wasn't even close. It wasn't even close, and there was 2 of them. So it's not, this is not uncommon. Because, you know, in a startup, there's so much stuff and there's so many things going on. Pretty soon, even if you knew it was wrong, you try to get it corrected, and it goes on for so long, finally you're just moved on to other things, and then you've forgotten about it. That just happens. That's the way, I mean, we're all human, you know? So it just, and all of a sudden you go, you know, I kind of remember that 20 years ago we had that issue, you know? So it can come back. What a good calibration looks like. So some of the main things, we've talked about this a little bit, is try to do it the best way possible without making it too much hassle of taking it out and sending it in. Nobody wants to do all that, and it's not necessary. So we use verificators, or we use really, really good equipment. We have, we use a lot of fluke meters, so we have one fluke meter that's $15,000 now. I bought them, they're about $9. Now they're 10, 12, 15. They do pressure, temperature, RTDs, thermocouples, and they're very, 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 very accurate. There's a protocol called HART, and HART is like, think of an English language where we can go in and program and change things. It's got that built into it. So we have some really, really, really good equipment. When I do a pressure transducer, we use that 85, let's just say $10,000 piece of equipment. Then we have a transducer that converts it from pressure to the signal the meter can read. That's usually around 17 to 2200. And then we have a hand pump that we can simulate it. That's another 12 to 1500. So around, you know, $15,000 just to do a pressure transducer. So we're kind of picky. A little bit excessive. I said I went to work for an engineering company. You know, and after I got out of college, I went to work for a factory, a manufacturing plant, and then I went to work for an engineering company. And all those engineers taught me so much about equipment, test equipment, and the importance of it. Otherwise, I didn't know before that. You know, it's all the different people's information that I learned. It was probably the most important part of my life was that 5 years. So having a verificator, making sure they're tested by an outside source, which is NIST, making sure it's accurate and right, and then documenting what it was, as found, as left it's called, and then checking the inputs and the outputs and all the setup to make sure it's right, and then also being able to do multi-brands with one person. That's important. Otherwise, you're calling out 2 or 3 people to do things. I always say, we have all this equipment, and it doesn't do any good unless you know how to use it. And the way I explain it is you get a skid steer and you put the guy on it the first day, and it takes him a month to finish and level out his lot. But you got the guy that's been doing it for 20 years, he can do it in 4 hours. Well, it's the same thing with this equipment. You don't just know it, you have to learn it, you have to understand all the different things, put it all together, and then be able to use it. And every application is just a little bit different, just like excavating or anything else. It's just a little bit different. Looks the same from the outside, but it's not. So what is a verification? We talked about calibration verification. So if you were to ask me, I would say a verification is something where you really can't even change anything. You're just checking it the best way possible so that you can make the most educated decision about it or the result. So a lift station, for example, has the pumps and they're pumping, but there's no flow meter. So how do you know what's going through there? Well, you use that drawdown. And we have one online, so if you guys want to use it, we have an online drawdown that you can put in the size of your tank, whatever you want to call it. It's a cylinder, it's a rectangle, what size it is, and then put down what the start level was, and the stop level was, and the time, and it'll tell you what the gallons per minute are, and then you can also do the fill time. So it's right on our website if you want to use that at Calibration Controls. What's that? Okay, thanks. All right. So lift stations are one of those where you're really just doing a verification to tell you what that pump is doing. Another verification would be using that transit time on a prop meter where we really can't do a calibration. So we're comparing it and then looking over time to see what's happening with it. So important takeaways, look at that. That was good timing. Important takeaways is NIST traceable for equipment to make sure that it's correct. Having knowledgeable people. We're a partner with you guys, so we're all working together trying to achieve the same thing, make our jobs as easy as possible. Having the correct equipment and the trust only comes over time, and then the MPCA requirement or fulfillments that you guys require. And that's basically it. So if anybody has any other questions. Sure, we don't have any cups left. Two questions. No? All right.
There we go.
Oh.
Is there any change do you see in the regulation on requirements for testing?
They do change them once in a while, but the basic structure is always the same. And that's something you would have to follow, and that's what these classes are about, where you guys go to and update and make sure things don't change. I don't really follow those as much because that's kind of your responsibility. I know that they have to be done every 2 years. And we surpass the calibration requirements by a long, long, long way. So